Hello, I'm Doug Craigen, the team leader for testing and benchmarking at Integrated Engineering Software. I've been doing this job for over 20 years and quite enjoy the challenge of finding out how accurately we can simulate many different electric, magnetic, and particle trajectory problems. I've recently been benchmarking magnetic forces and was quite surprised by some of the things that I was seeing in unusual situations. Notably, I was seeing pieces of steel repelling away from magnet assemblies, and I thought, this doesn't feel real. It's not something that I would have expected. So I sent some ideas and proposals to Dexter Magnetic Technologies asking, is this actually real, or is there a problem with the simulations that I need to track down? And in response, they actually built it, sent me a picture of the steel hovering, and then sent me the assembly. So that's what you see sitting in front of me here, is their manufactured magnet on the base, piece of steel in the middle sandwich, and a thin sheet of steel that's hovering above the first one. For my own curiosity to pursue this, I then cut some steel out of soup cans. So these are not manufactured to the high precision that Dexter did, but you see on top of that whole assembly another piece of steel hovering again. And there's a few more pieces here that I'll use in subsequent slides along with this, where you'll see that this washer, instead of hanging on the paper, will hover upwards when I move it over the steel assembly. So I'll be zooming in and showing all of these things in much more detail and explaining why it is that this actually happens. I hope you enjoy the rest of the show. On the right, you can see a video of me playing with the device, both the original pieces received from Dexter, along with the sheets of steel that I cut from soup can lids. You may notice that the precision cut pieces from Dexter work a lot nicer than my soup can lids, but the soup can lids especially help show something else that I was told. When Bojang sent me the device, he also told me about a device called a sheet fanner. And a sheet fanner is used to separate the edge of a piece of steel from the top of a stack. The idea being that it's hard to pull the top sheet off a stack of steel, but if you put a magnet nearby, which creates magnetization parallel in the sheets of steel, they will repel each other, and if you do it right, you can get just the top edge to lift up so that the top sheet angles a little bit. And you'll see that kind of thing happening when a misalignment occurs. The sheets of metal can do funny things, but fanning upwards at an angle from one of the edges is one of the things that tends to happen. On the left, you can see an AMPERES model of the device, along with me holding the device and looking at it close up. You'll see a plexiglass structure that I built to contain the horizontal motion. This is a loose structure. It is not restricting the motion, although you'll see that my soup can lids tend to jam a little bit against the jagged edges of the plexiglass. Between the jag of my cutting and the jag of the plexiglass, there's room for some mechanical friction. But otherwise, they tend to just float up and downwards, and the lids are only in contact at one or 2 points with the structure at any time. The plexiglass is put there simply because although AMPERES predicts a repulsion vertically, it predicts that a force will develop horizontally as soon as there is a misalignment. So this is kind of like having a ball sitting on the top of a hill. Although it balances perfectly at some point, as soon as you misalign it, it will start to roll down. And similarly, if you leave these just hovering in free space, within a very small time, they will snap over in one direction or another quite randomly. So the plexiglass exerts very little force because as soon as the sheets of metal start to move a little bit to one side or the other, they're stopped before the force gets very big. From my initial observations of tiny magnetic repulsion, I wanted to get to something that would actually be observable, and I made extensive use of AMPERES parametric and playing around with models until I thought I could get there. I eventually came up with what you can see here, which is a 3 by 3 by 1 centimeter neodymium magnet. On top of that, the same dimensions, a piece of 1010 steel. And I made these choices based on things that, as far as I could tell, would be readily available. In order to study this, I first put the device together as shown like this and asked the AMPERES what the force was. And in fact, the vertical repulsion force predicted far exceeded the weight of the sheet. That said that it would lift up above the surface and we would see how far it went. All it does is it moves the steel and magnet blocks downwards rather than moving the sheet upwards, but same thing. When I plot it out and make a horizontal line corresponding to the weight of the sheet, and given that we start with a gap of 0.5 millimeters, that says that the hovering distance or the levitation distance of the sheet above the steel block would be about 3.5 millimeters. And if you look at the videos and photographs, keeping in mind that the steel block is 1 centimeter tall, you'll see that indeed the hovering distance is about 1/3 of that. So what is going on here, and why did my intuition fail me so badly initially on this type of phenomena? To understand that, I simply used the field visualization tools in AMPERES. On the left, you see the lines of magnetic flux, which offer a lot of insight to many problems. We see the flux coming out of the magnet, dividing towards the top and the bottom. Of that goes out the top, some returns through the block of steel, and some bends into the sheet of steel and returns through the sheet. The key thing is that these flux lines enter the steel on the same side and exit the steel on the opposite side, so that both the block and the steel sheet magnetize in the same direction, as shown on the right with the arrow plots of the M field, and that direction is opposite to the magnetization of the magnet itself. This will lead to repulsion, as we'll see on the next slide, but what it means is that the two pieces of steel both attract toward the magnet, but they both repel each other. So when you're looking to figure out what is the net force on the top piece of steel, you have to add both of those together, an attraction and a repulsion. And depending on the details, one or the other may dominate. So if you change the model parameters a little bit, the thicknesses of anything and so on, you can easily see this flip around. So it's not an automatic that something looks roughly like this is going to lead to a repulsion effect, but it is something that happens quite readily over a wide range of properties. To demonstrate the magnetic repulsion between parallel and anti-parallel magnetization, I took 8 disc magnets that I have on hand and put them all together to make a long magnet, and then I broke them into the middle to make 2 shorter magnets. When you pull them straight apart, they are now end-to-end the same magnetization, so if you move them a little bit apart horizontally and then to be parallel to each other, the magnetization is in the same direction, and you can see in the video how they repel when I do that. If I then flip one of the magnets around to be anti-parallel to the other magnet, they attract together. And of course, the main thing that the magnets try to do is to rotate. So if I put them in a position where they're free to do that, they will rotate to be anti-parallel to each other. To get a visualization of all of this, I again built the model in AMPERES. I made up my 4 discrete magnets on each side, put them parallel and anti-parallel to each other, and made pictures of the magnetization in each, showing which it is, and the flux lines coming out of one set of magnets. And you can see that when the magnets are anti-parallel, the flux coming out of one is pulled over towards the other, and a lot of the flux returns through the other. But when they are parallel, the flux repels away. And a lot of people visualize mechanical type problems by thinking of flux lines as kind of being like flexible wires or something that they push it towards or away from each other. When you see the flux lines pushing away from the other magnet, that means there's a force in the away direction. Once I understood the basics of what was going on that creates a magnetic repulsion, it became easy to conceive of other proposals for devices that would repel in a similar fashion. The problem is that I don't have materials on hand to test most of those, and they're more a curiosity rather than something of practical use for me right now. Maybe some people watching this video can dream up useful devices based on these principles. One of the things I do have readily on hand is, of course, things like washers, nails, and so on that are well known to interact magnetically. So I was thinking about the washer in particular and thinking, well, it's going to have the same dynamic as the sheet of steel has. However, when I ran it in AMPERES in the same configuration, I got no net repulsion. So that was a non-starter. So I thought, well, let's try it differently. Let's try turning the whole assembly on its edge and see what happens if I approach that way. And AMPERES then predicted that there would be a force away from the steel and the magnet on the washer. And when I plotted out the M fields, of course, I saw the same thing as in my other model. In all these cases, there is the same effect of the magnetization in the two steels being parallel, hence repulsive. The only question is in the fine details whether it's going to be that repulsion or the attraction to the magnet that will dominate. And in this case, when I tested the AMPERES prediction, it worked out beautifully. Although it's very sensitive, it's far more unbalanced in the horizontal direction. But when I taped a washer onto a piece of paper so that I could control its motion a little bit and fed it towards the edge, what I found is that it would indeed repel away in both directions, as AMPERES had predicted, that it pushes back towards my hand and pushes up in the air. And what I also show in the quick video here is that the transition to pushing away to pulling together happens very suddenly. And in fact, because I haven't secured the magnet, it happens especially suddenly because the repulsion force soon becomes an attraction force and the magnet pulls towards a piece of paper, and that then becomes an even smaller distance and a much larger force, and holding it as loosely as I am, it just whips over and instantly latches onto the magnet. So many more examples can be thought of, but I wanted to close with some simple thoughts here, and that is that, well, what I've been showing is related to a second order effect, that is the interaction between the induced magnetizations in two steels. There's no reason why only induced magnetization could do this. there's no reason why one couldn't construct a magnet such that it did both. And so there's no reason why one couldn't get potentially even much larger forces by constructing magnets such that the actual strong magnetization was what was giving the repulsion effect. So I have tested this on a small scale, but don't have anything large to demonstrate right now. I'm leaving this as an active project for the future to hopefully follow up this video with one demonstrating how one can use simply a magnet to repel a piece of steel.